Hey there. So in the previous video, we took a look at how the instructions are encoded as per the RISC-V instruction set and how they are placed in the memory. Now we kind of only proved the fact that the encoding complied with the RISC-V instruction set. In this video, what I want to do is quickly run an example of an assembly program and then maybe also explain parts of it. So what you see on the screen here is an example of an assembly program that we'll kind of type it out and experiment with. So what you see here is we are loading x1 with 5, which is happening at this point, right? And then on the next line, we are loading x2 with 0. And at this point, we are loading x3 with a 0. Oh, sorry, x2 we are loading with a 1. So that is the immediate value here, the immediate value here, and the immediate value here, right? So now these three lines, and we'll come to this and this in a while, right? So these three lines are also assembly instructions. Again, these are assembly instructions for the RISC-V RV32I instruction set. So we're specifically following that just because life becomes a little more easier. At this point, I should also mention that what we learn here becomes very crucial to understanding and reasoning about the C language later on, right? So, okay, let's continue. So what's happening here then is we are doing x3 equals to x3 plus x2, right? So we are just essentially saying 0 plus 1 based on these two. Then x3 will be updated to a 1, right? And then at this point, what we are doing is we are saying, hey, reduce x1 by a factor of 1. So this becomes a 4 at this point, right? And this instruction here is essentially saying, hey, we are going to branch when not equal to 0. But what is not equal to 0? x1. So the CPU now, what it will do is it will say, hey, is x1 0? If it is not, I am supposed to branch. Branch is essentially a jump. And branch instruction is one of those instructions that can change the program counter value, right? So the branch instruction then says, hey, I'm supposed to go back to something called loop, right? And what is loop? Loop here is called a label. A label is just a convenient name to a location in the memory, right? So for example, this is also a label, right? There's nothing sacred about start as a keyword and label loop as a keyword. There's nothing sacred about it. We could have named this XYZ and this as PQR, which we can try, or actually which you can try. The idea is that you just have a name here, some name followed by a colon. So if you see something followed by a colon as first thing on the left side of the file, then that's a label. And labels are just that, they are pointing to a memory location, or representative of a memory location that we later want to use. Okay, if that was confusing, so here's what it means. So we are supposed to give here, we are supposed to substitute here the offset. Offset to what? Offset to where we want to jump. So we wanted to jump 4 units back, 8 units back. And remember, the 4 and the 8 choice is coming from the fact that in RV32, each instruction is 32-bit wide. And this was kind of discussed in the previous video. So the idea then is we would want to go backwards at this point. So this loop value or the offset here needs to be -8. And now this is not part of the assembly language as such. Well, actually, it is part of assembly language. What I meant was this -8 manipulation, the fact that -8 gets put there, that is taken care by the assembler. And the labels are what assist the assembler to figure out what value needs to go here. Now, if all of this is sounding confusing, just hang in, because we'll kind of run an experiment and all of this will be clear. Okay, so if we are done with this, well, let me move back to our desktop. And also, at this point, I must say, if you would want to follow, let me just quickly, yeah, let me just very quickly share my screen. Yeah, perfect. Okay, so what I have to mention at this point is, if you want to follow along these experiments or reproduce, make sure Docker is running, right? That is one essential thing. And now my Docker is running. So what I'm going to do is I'm going to launch, let me just quit VS Code so that I can launch it from scratch. So launch VS Code. In my case, it has gone ahead and connected with the Docker, what do you say, environment, but let me do this. Let me open up a new window. Let us kill this, right? So in your case, you would see something like this, right? And if you have followed the video 0, which guides on setting up the lab environment, then you should have the Docker as well as the right extensions for VS Code installed. Now, what I will do is I'll go to this remote explorer, and from within the drop down here, select the dev containers, and then we'll see that there is C Ninja Linux, right? And what I'll do is I'll hit this arrow here, which is this particular arrow, right? So just hit that arrow, and uh, and you will see that it connects with Docker. Now this should sound like a familiar site, right? So all these things should be familiar from previous video again, and video number 0. You might get an environment which is somewhat like this. So I need to turn on the keycaster. Okay, perfect. Let me get myself out of the way, right? So that you can follow along with the keystrokes. So if I were to press Control and tilde, then I get the terminal, right? And you would see something like so. Control and tilde. If not, then Command Shift P in my case, and I can type terminal here, right? And then open up which one? I think it is open new external terminal, maybe. Okay, we don't want this, but this is also all right. We wouldn't want this. I'll just continue to work with this. I suppose you can also get a terminal from here. Right, so you can do new terminal, and okay, there is another terminal. Okay, fine. So what we are now going to do is cd into the test directory, because we want to work on top of the example we saw yesterday. And if you see, there is the test directory here. All right, and you should see something like so. You can click here, this will open, and click on main.s. So this is one of the assembly programs that we used in the previous video. And what I'm going to do now is I'm going to cheat a little bit, because I already have, instead of writing that assembly program, I'm going to copy it over and put it here, right? So now we see, okay, start, add, x1 gets loaded with 5, blah, 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 so on and so forth. Now, what I did not do on my screen, the sketchpad, is I did not put this last instruction, and I'm going to put it here. What that instruction does is, it will become clear in a while. Okay, let me go ahead and save this. So from this point on, first we are going to essentially analyze each of these instructions and their associated bit pattern. So once we have saved this, we'll just go ahead and do a make. And remember, towards the end, we have kind of the hex content of memory location printed. So this binary has about like 1, 2, 3, 4, 5, 6, 7 instructions, and that makes sense. 1, 3, 6. Oh, sorry, 1, 3 is 4, 4, 3 is 7. So we have 7 instructions, and encodings of the 7 instructions. That's a check. Now, much like the previous video, we're going to pull up our web browser and then type RISC RISC-V encoder encode decode. Once we do that, we get these results. We'll go to the second one, the GitLab one. because it straight leads to the application, this one. And now what we are going to do is one by one, let me just put this on the side. So, and then this on this side. Okay. So one by one, we are going to analyze all of these, right? To ensure that it's actually generating what we expect it to. All right. So add x1, 𝗁𝗵𝗽, that matches with this. Again, not clear. Let me just point back. Okay. Cannot. Oh, actually I can. So yeah, this is this, right? And okay, so that we have verified. Now let's very rapidly go on verifying the other. So x2, 𝗁𝗁, x2, 𝗁𝗁. Let's go ahead with the next one. So somewhere some interesting things will happen. So x3, 𝗁𝗁, x3, 𝗁𝗁. Right, now we're left with 4 of them. So let's just do all of those. So x3, x3, x2, add x3, x3, x2. Correct. Then we go here and we go here. x1, x1 minus 1, add I, x1, x1 minus 1. What you can do is when you try this example, you can actually pull up the RISC-V card, the green card, and then kind of compare the opcodes, right? That would be a nice thing to do. And we'll also go back and do some more confirmation with the confirmation of the instructions. So bnez x1 x0 minus 8. We kind of do not see this instruction. Instead, we see branch not equal to bnez x1 loop. So it turns out bnez is something called pseudo instruction. It's not an instruction that RISC-V ISA gives us, but the assembler kind of helps us in a way to create like a short form. So the bnez x1 x0 minus 8, what it has done is, remember that x0 is always tied to 0. It's hardware it is kind of tied to the value 0. You cannot write this and update this to any other value. So what the assembler would do for us is it will understand that bnez actually means bne, okay, x1 comma x0, it will substitute on its own. And remember, then I was talking about the loop being an address or a placeholder of pointing to a memory location. So it was pointing to this. Now what it did was, the bne instruction requires an offset to where you want to jump from the program counter. We'll come to this in a while, but what we are saying is, hey, if we were to execute this instruction, we would want to jump back to this instruction, which is 2 units away, and 2 units away would mean 4 bytes away, 8 bytes away, right? So this instruction here is 8 bytes away from this instruction, and that's where we get this minus 8 value from. Minus 8 means go backwards, and go backwards how much? So 8. So that's what is really happening here. All right, so what is this instruction? So first off, let us just go and decode that as well. Right, so it says JAL x0, 0. So JA again is a pseudo instruction that translates into jump and link x0 with 0, right? We'll come to this in a while towards when we look at the RISC-V card. We'll come to this in a while. But what is happening here is J dot means jump in the current location, right? So let me just do my screen share again, because for some reason not working well today. Okay, perfect. So what I can do now is sketch. So this dot here essentially means this same location, right? And so what you see here is we want to jump at an offset of 0, right? And then there is something special about JAL, the jump and link instruction, that we'll take a look at in a while. Okay, so let's come to the JAL in a while, what I'm wanting to now do is show you a demo first of how this thing executes. Right. So we have a terminal here, which is great. We would need one more terminal. So I'm just going to go ahead and press the plus button here, and then I'm going to drag and pull it here on the side. Right. And the reason to that is I would want to have like a bigger space, which you'll see in a while why. Okay, so first off, let me just in this terminal go to the test directory, and I'm also here in the test directory. So what I'll do is I'll do make debug. And from the previous video, you can recall that make debug will launch the quick emulator, the QEMU, and then run the RISC-V machine on it and load our program, this main.elf file here. Okay, let me, right, so the main.elf file here. So what it'll do is it'll load that into QEMU and run it, right? And what we want to do is we want to cache the processor even before it executes the first instruction. If you see something like this, we wouldn't care about it, so we'll let it go. In this new terminal, we'll do make GDB, and we'll talk about what GDB is, what QEMU is, what make is in later videos. That's also coming. But for now, trust that this will launch the debugger. And the debugger here is the fancy one, the dashboard, GDB dashboard, which again, we looked at in the previous video. So, okay, what is going on here, right? And just to recap, these are the CPU registers, and know that these are using the ABI names. And then by our experience, we know this is X0 because I told you so yesterday, well, not yesterday, but in the previous video. And then this is X1, and this is X2, this is X3, right? And we are interested in X3, X2, X1 because, well, we have these here, right? Okay, so with that, well, I suppose the other thing that we should take a look at is we are right now here. And remember the label, this and this are simply representing the location of the first instruction that follows them, which is this. So start is essentially representing this, and this is at the memory location hex 8 all zeros, and that is also confirmed by the value of program counter. So program counter is pointing to the first instruction here. Now again, why program counter is at hex 8 all zeros? That has to do with where the memory is in the quick emulator board, so to speak. So this board here, this machine, the memory for this machine starts at hex 8, all zeros. And how many zeros you can just infer from here. Okay, so by the way, just trust me that all of this is true, and you can also verify it. Okay, so what we are now going to do is we are going to use the mighty power of the ni instruction to kind of step through. And my request is, as we step through, just keep track of the register values here, right? So remember, this is x1, x2, x3, so we are interested in this. So what we expect now is x1 should become 5, so which is this. So I'll just go ahead and do an ni. So this indeed became 5, right? And note that the program counter has incremented by 4. That should again reconfirm that each instruction is 4 bytes long. Okay, so and what we see here is the instruction to be executed that is highlighted. All right, so now I'll do ni again, and x2 should be set to 1. So x2 is set to 1. Right? And then we do ni again, and something happened. What just happened? Okay, we are now executing the we are about to execute this instruction. We executed this, x3 was supposed to become 0, x3 is this, that was already 0, so it's not highlighted in green. Notice again, program counter has moved to the 4th instruction, so 0, 4, 8, and C. So that's the C. Now what will happen next is, first off, the moment I execute this instruction, you will see that this gets updated to 1, x3 becomes 1. So let's do that, and indeed x3 became 1. let's execute this, and we'll notice that x1 reduces by 1. So that's it should become 4. It became 4. And then we do ni again. Now this is the interesting bit. Notice the value of program counter. It is, let me just write it here. So it is hex 14, right? And now what will happen is we mentioned that this translates to branch not equal x1 x0 minus 8, right? So when we do like a minus 8 here, well, this is in hex. So first off, let me just get rid of 4. So it would be, so this should go back to being in hex C. Hopefully I've got this math right. I cannot do mathematics very well in decimal, but I can do it in hex, and we'll see how well. Okay, so let me just hide the annotations and let's go back here. So my claim is when I execute the ni instruction now, PC should go back to being, all of this number and then 0C at the end. Let's just see. Okay, perfect. So if you okay. Oh, okay, sorry, wrong. Yeah, right. So if you see, this has now become C and this is C. Also, I have to mention that I ignored everything in front here, which was all of this value. I was just dealing with the last 2 nibbles, so to speak. So, okay, anyways, hopefully this convinces you that there was a jump taken. There was some sort of program counter being reset to, not reset, but set to the instruction here, right? And now what I'll do is I'll continue to do an ni, right? And you'll see that this value is going on decrementing. If I do ni again, oh, sorry, if I do ni again, okay, program counter is incrementing. I'll do ni again. Okay, this is incrementing, and then I do ni again. Okay, this has decremented to 2. Let me just keep on doing ni. Okay, now this is going to be interesting. Okay, great. So x3 here, again, let me bring up my annotation, get rid of the previous ones. So x3 here has become 5. So at the end of it all, we started off from 0 and then we went all the way to x3 becoming 5, right? And what you have now seen is the x1 value here has come down to 0, which means this condition here now, branch not equal to x1 x0 minus 8, x1 and x0, they're not same anymore. So essentially they are, well, sorry, they're not different anymore. Both of them happen to be 0. This we decremented from 5 down to 0, and x0, as I mentioned, is always it is always 0 on a RISC-V machine. So both of them are 0. So now the branch should not be taken, right? So what will happen is it will fall through and the assembly program will execute the jump j dot. All right. So let me then go ahead, get rid of all of this, execute an ni. And if you notice now, it is pointing to this instruction, right? This instruction right here, the j dot. And a program counter is like 8 all zeros 1 8. Now the thing is, every time I do an ni, the control just stays there, right? Control meaning the CPU is just looping in one place. Again, it's just going back in circles here, and that was deliberate. If I had not done it, then once it comes down from here, it wouldn't know what instructions to execute. So it would execute any of the garbage that's available, which is like 0, as you can see here. Right? You can see here. And at this memory location, there is nothing, and so it would go ahead and execute that, which is just an arbitrary number. By the way, at this point, this is an arbitrary number, which is 0. So it would go ahead and treat that as a instruction and mess up the CPU. The CPU would do whatever that thing, that content in the memory location is interpreted as an instruction. So it would assume that it's an instruction and then go ahead and try to execute it. That was the point. In case I haven't already confused you. If I confused you, I'm really sorry. I don't want to re-record this video. So, okay. Anyways, so hopefully, you know, this kind of hammers home some learnings, hammers home the point that, you know, we can write some text here that the compiler, and what compiler is we'll look at again in another video, but I did mention something about assemblers. So assembler will take this content and then convert it to, you know, zeros and ones, which are encodings for instructions essentially, and the CPU is completely capable of executing those. And then we saw that registers, internal registers, get modified. Okay, cool. So now what I want to do is I want to go back to RV32i instructions and then just go over all the instructions that we have used. So let me pull up the browser. Oh, actually, let's just first quit all of this. So in GDB, we type Q to quit it, followed by a Y. At the bottom terminal, I can use AX to quit the QEMU. Okay, back to the browser. Where is the browser? Okay, back to the browser, and we look for RISC-V card. Let's just look for that, and then we just go with whatever comes up first, hopefully. So there are 3 types of instructions that we want to, 4. We want to look up addi. Okay, we want to look up addi, we want to look up add, bnez, most likely we won't find that, and we want to look up j, which also we won't find, may not find. Let's see. By the way, I haven't taken a look at this document before trying to record the video, so it's live recording. Okay, so look for addi. So addi is here. First off, I think I'll need to zoom this if I can. Very nice. Oops. Sorry. Okay, so let's see. So addi is right here. Oh wow, color changed. Very nice. Okay, so the addi instruction is here, and the addi instruction means this, that it will take the destination and take the source one and add the immediate value. So destination is this, source is 0, and then add immediate. So for those reasons, x1 becomes 5, right? Similarly, also, well, I should mention, take a look at this. So this is the type of instruction, and addi happens to be I type of instruction, immediate value. This again should reinforce our understanding from yesterday. All right, let me get rid of all of this. Now what we want to look at, the next instruction, is bnez. That I don't think we have. We don't, but we saw that bnez translates to bne. So bne is SB, so I think that's signed branch or something like that, stored branch or signed branch, but it's a branch type instruction. And you see the description here as branch not equal. Okay. And then now the important bit is I got to zoom this in. If only it lets me. Yep. Okay, let's go up. bne. Okay. Let's get rid of this. So bne is here. It says branch not equal. And you see the if condition being stated here. So it says if the register source 1 is not equal to register source 2. So remember this translated to bne, bne x1 comma x0 minus 8, right? So this was source 1, source 2, and if both of them were not equal, then what would happen is it updates the program counter here. And then it updates program counter with what? So it updates the program counter with the PC value plus the immediate value. And it's represented here in a little cryptic way. We'll come to the details of that also much later. But trust me that it is modifying the program counter. And so at this point, it sets program counter equals to program counter minus 8, as a result of which it would go back 2 instructions back. Right. Okay. And then we saw that okay, let me first off actually get rid of all annotations. So we now take a look at the J dot. So remember, it translated to JAL x0 minus 0, not minus, but comma 0. So let's look for the JAL instruction. Again, remember J itself, J dot, J itself is a pseudo instruction. So here you go, JAL, jump and link. This instruction is a little special. And so JAL. Okay, the color changed again. Congratulations. I don't know how to change back the color. Let me see. Brush tool, yes. Show toolbar. Which color do we want? Let's take red. Get out of here. Yeah. Okay. So JAL. Nice. So the JAL is jump type of instruction. UJ is, I think, unsigned jump or something like that. I forget the details of it. It's an homework for you. So, okay, what is happening here is the destination register, wow, okay, gets the PC plus 4. So whatever program counter was here, the destination register gets that value, and the program counter is incremented by the immediate value. Right. So the immediate value here is 0. So program counter is not incremented by anything. And then we are saying that, hey, destination register, store the program counter plus 4. So this address plus 4 in that destination register. But destination register is 0, x0. So the x0 register, because it is tied to the 0 value, you cannot write to it. And because you cannot write to it, this PC plus 4 value is discarded. I mean, you write it to a 0 register, which means nothing. So the JAL instruction, the J dot, essentially expands to JAL of this kind. And this results in the program counter kind of continuously being incremented by 0, and it stays at the same location. And this is like one of the ways in which you halt the CPU, so to speak. You just make it spin in one place. So yeah, hopefully we learned, hopefully you learned something about the assembly language as part of this demo here. So let me get rid of this, and then also this. Okay, yeah. So let me get rid of this. So yeah, hopefully you learned something about how assembly programs are written. Again, the choice of start here is immaterial. It could have been anything else, and also this could have been anything else. And right, the spacing here is no problem. We could have done this. We could have done this. That's not a problem. Yeah, all of this just means the same thing. But as you can see, it's like not readable at all. It's hard to make out what is going on. By the way, this should be updated to this, and to prove the point that it is still the same program, let me first save this and then go ahead and do make clean. So everything is wiped out, and do make, and we get the same program. Right? So label names, well, there are rules around label names that I'll leave for you to find out. But label is something that starts on the left, has a colon at the end. Instructions straight come from the where is our, so instructions straight up come from here. Okay, don't want to go into my history. Okay, so the instructions come from the RISC-V card, and the labels are here. J dot are pseudo instruction, bnez pseudo instruction. And yeah, that's about it. So hopefully you've learned something about the assembly language again. And I will see you in the next video where we can go over, remainder of the files here. We can explore all of these a little bit so that you're comfortable with what all happened as part of the test directory. And then slowly we'll move towards the C language. Cool. So I will see you in the next video, and thanks for hanging around this long. Bye-bye.